The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Before we start, just a few words about the book and the way I teach and reading assignments and stuff like that. So, the book was written by a very debonair professor at MIT by the name of, and a very brilliant, Jim Williams, Professor James Williams. And in my opinion, it's the most complete book for dynamics for undergrads on the planet, right? There are graduate books, grad school books, which have more stuff. But this is the best reference book I have seen in how complete it is. Now, and I haven't found any book better. So it's with great pride that we use this book as our text. And he wrote it about 10 years ago, and we kind of brought it back, right? And he's a very interesting man. In fact, at some point, I might ask him to come and give a talk in the class as well. There's a picture of him in the back. Now, the way that we're going to use the book, though, is not in the traditional sense, of the way classes are taught. We tend at MIT not to go by the book, because we modernize, we change, we invent new ways of teaching stuff, and we adopt other people's techniques and so on. But everything that I'll talk about is in the book, right? So the way we'll follow it is in two ways. First, I will give you reading assignments which will not correspond exactly with the book. Which will not correspond exactly with the way I teach it, but when you read it, if you really understand what I'm saying, you'll see what the book is saying. So the essence is not different, but some of the terminology, etc., is different. I'll tell you what that difference is in a minute. The second thing is we will use the book for problems and the solved problems that are terrific. So I suggest, in fact, I insist that you read the book and the sections that I recommend in the class. But the third point is that we will give you handouts. These are things that I wrote up last year, because what happened last year was that, I was doing the class differently, and because of a snafu with the publishers, the book didn't show up. So I just wrote up a kind of a parallel textbook, not that many pages, but 50 to 100 pages. And we'll give those handouts to you in bite-sized chunks, and we recommend you read those as well. So now, in the book, the reading assignment from the book, so your reading assignment is going to be like this. I want you to read chapter 1. And I want you to read chapter 3. It might seem like a lot, but actually it's a very quick read. Chapter 1 is the history of dynamics, and it's a gorgeous piece of, it's a gorgeous summary of, several hundred years of dynamics, and strongly recommend you read it. The thing about some of these subjects is that Coriolis force, why on earth is it called Coriolis force, right? And if you read the book, if you read the history, it gives you some reason. We write things in a way because of the way they evolved over history. And if you understand the history, you'll understand better why we write things in a certain way. It'll just make more sense, trust me. Chapter 3 is on kinematics. Now, the fundamental difference between me, or the way I teach the class, and the way the book does it, is in my maniacal insistence on using frames of reference. Okay? So, for example, I would never write this. Okay. I would say I would insist that if you are taking the derivative of some vector, you specify which frame you're taking it with respect to. Okay. And this is a modern way of doing it. The book would write the vector that way. It would write the derivative like this. And the context of which frame would be, it would come from the context, right? Which is okay, that works, because you need to keep track of the context. But the reason I prefer to do this is, first of all, even I get confused about context. And the second thing is, this works when you have two frames, right? But when you have multiple frames, the whole relative, relative is with respect to another frame. But let's say you have three frames. So relative, the whole relative concept becomes confusing. But if you specify the frame and say it's with respect to A, it's very clean. So fundamentally, that's kind of where the differences creep in. And once I introduce this notation, you notice just the way I proceed with things is slightly different. But when you read the book, you'll see what the differences are, and you'll understand why I do it this way and why Professor Williams does it the other way. But there's no fundamental difference. Yeah. That's actually a much deeper question than you might imagine. Let me explain why. All editions are good except the editions which had typos. Okay? So the reason we had a snafu last year was because Professor Williams went to the coop and pulled out some of the books there, and he found they had typos, significant typos. So he and I started, screaming at the publisher, and the publisher made one mistake after another, and it took us about 3 months to get the final textbooks in. So there are textbooks floating around with typos. And perhaps, Sanjay, you can just put a little note on how to discover whether your edition is a bad edition or a good edition. Okay, so if you inherited it from someone else, you might have a bad edition. All right, but if you have a good edition, I don't care which one. Okay, Ajay, any comments? Mm-hmm. Yeah, so if it's 2006 December, you're good for sure. Yeah, anything you bought from the coop now is good. But if you inherited anything published in, say, October of 2006, it has some evil stuff in it. Okay? So, if you take this, you know what a gimbal assembly is? A gimbal, right? Anything with a lot of degrees of freedom, right? This earth thing here can rotate this way, it can rotate this way, and I can rotate it this way. Right? It's got 3 degrees of freedom. This is a very typical dynamic system. In space systems, this is standard. So the moment you get to 3, the whole concept of relative, relative to the first one or the second one, right? The whole concept kind of breaks down. That's why I prefer to write A, B, and C and just kind of flesh it out. So that's the difference from the book, all right? But the handouts that we're putting up on the web today, they say it in the right way, or say it in a way that's compatible with my thinking, and we should be good with that. Okay, so these are the reading assignments. Do read these and the handout. So let me write that as well. Okay. Now, I have one favor to ask of you guys, because I left one segment of my notes at home, and it'll be good for you to help me out with this. Tell me what the transformation, if you have 2 frames, A with, A1 and A2, right? I may not write A1 and A2 each time I do it because it's repetitive. You'll just assume it's okay. If you have 2 frames, we have those transformations. Can someone read out the transformations to me? This is theta. Can anyone read the someone, please, from your notes? First, tell me what A1 is and A2 is in terms of B1 and B2. And then tell me what B1 and B2 are in terms of A1 and A2. Andrew, do you have your notes? Anyone? Yeah, just convert it to A and B for me. I'm writing it as A and B. All right, just the trick. One is going to be negative, and one is, it's skew symmetric, right? I mean, this is going to be negative, this is going to be positive, these two are positive. That's the pattern. Or you can switch them. If theta gets switched, these negative, positive things switch. All right, that's just a pattern you want to look for. So what is B1 and B2? Yep. Oh, yeah, sorry. Yeah, what's this? You know what's going to happen? This negative is going to switch. That's all that's going to happen, right? Because sine theta is, sine of minus theta is minus sine theta. So these two will switch. So I'll just write it down quickly. And tell me if I'm doing it right. Okay, we'll keep this as a reference, and we'll keep coming back to this. Okay. All right, so here's where we're going to start. We'll start with where we left off in the last class, obviously, which is we examined the velocity and the acceleration of the spider on the frisbee as the frisbee hurtled through space. We did it in 2 dimensions. So the center of the frisbee was moving, right? And the frisbee was rotating, and the spider was also simultaneously, with respect to the frisbee, it was walking in a straight line away. And we computed the velocity and the acceleration. So if someone could help me here, let us, so in fact, let me just draw the picture for you. We had a frame, which was, we called it Earth, right? And we called it, I'm going to make it A now, A and B. All right, I'm not going to call it E and F anymore. We had a frame B, and the frisbee was on this frame. The distance, we call this O. We call this point P, and we call this point where the spider was S. Frame B. We call this distance U. We call this distance V. And we call this length. What do we call it? Locally as L. And we call the angle what? Theta, I think, right? Actually, we said E and F, but I'm just going to change it to A and B. Okay? Because F is also used for force, and eventually it'll get confusing. We're not at forces yet. We never considered a force in analyzing this. Why did we not even mention the word force in analyzing this? Anybody? I mean, we are in dynamics, yep.
We haven't given anything a mass yet?
Yeah, there's no mass. It's just pure kinematics. It's all geometry. We're trying to figure out, as a function of theta, theta dot, theta double dot, L, L dot, L double dot, U, U dot, U double dot, V, V dot, V double dot. We're trying to figure out what the acceleration is. Later on, we might put a mass and say F is equal to ma or something, right? But we aren't there yet. Okay, so this is the picture. Now, what I'd like you to do now is read out to me what that final acceleration was. Actually, both the velocity both the velocity and the acceleration. But I want you to replace E and F with A and B. Any volunteers? I just want one person. Yep, go ahead.
All right, so velocity.
A, how should I write it? Right. So let me ask you a question. I'll come back. I just want to ask something. Does a rigid body have a velocity? Yes? It's a trick question, actually. I want you to say yes so I can correct you. Say it again?
Is the rigid body static?
It doesn't sag. It's rigid. You should sag, right? S-A-G, sag. What did you say?
Static?
Static. Oh, no, no, no. Assume the rigid body is moving. Can it have, does the whole body have a velocity? How does that work? Think about it.
The center of mass can have some velocity with respect to a different.
Right. So good. So here's point number one. There is no such thing as a velocity of a rigid body. There is a velocity for a point on a rigid body. It may be by coincidence that all the points on the rigid body are moving with the same velocity, but there is no such thing as a velocity of a rigid body. Get it? This thing doesn't have a velocity, right? Every point has a different velocity, right? It's like saying, what's the position of a person? Well, what? The central mass of the person? Yeah, okay, I can give you a position, right? But they can have different velocities. So when you talk about velocities, the right superscript is always a point. Get it? In this case, it's the center of mass, so that's spider that we care about. Okay, only a point has a velocity on a rigid body in a frame, whatever. Make sense? Okay. So, go ahead. Actually, let's break it out. A1 U dot, yeah, plus A2 V dot. I'll help me write it this way. Then what's the next term?
Okay, so then A1 L dot plus A2 L dot.
I'm going to write it this way just to point something out to you, okay? Okay.
And then minus A1 theta dot L sine theta. And then plus A2 theta dot L cosine theta.
I just wrote the same thing. I just bunched the terms differently. Okay, so this is what we derived as a velocity. All right, tell me what the acceleration was. I want you to break it up like that. And I know what it is in my head, so.
All right, so A1 U double dot. And then add to A2 V double dot.
Mm-hmm.
Plus A1 L double dot cosine theta.
Any other L double dot terms?
Okay, then A2 L double dot sine theta. A1 or negative A1 L dot theta dot sine theta.
Sine theta?
A2 L dot theta dot cosine theta. Added.
Did we consolidate some of those terms? The L dot theta dot, does it show up again? Shows up twice, right?
Yeah.
So I can put a 2 here.
Yeah.
Okay, and so then the other one is 2, A2, and then L dot, theta dot, cosine theta. And then we have one more set of terms.
A1 theta or negative.
Mm-hmm.
L sine theta. And then on the bottom, you have A2 theta double dot cosine theta.
Is there one more term?
We have theta dot squared term.
Oh yeah, we missed that. Okay, where shall I write it? I don't have space. Ah, forget it. No, I'm just kidding, I can't do that. Okay, give me the other term. I'll put it here.
Okay, so negative A1 theta dot squared
Negative A1 theta dot squared,
L cosine theta.
L cosine theta,
And then negative
theta dot squared, yeah? Yeah?
and then negative A2 theta dot squared L sine theta.
Okay, so these are all the terms. Okay? You miss anything? All right. So I put them up for two reasons. One is towards the end of the last class, I was trying to point out a pattern to you. That's the first thing. The second thing is, I want to keep a record because I'm going to resolve this problem using some additional math later on today. And I want this around when we get there. Okay? So first, let me show you the pattern again. Let's look at this guy first. The velocity. So what is this term? What was the pattern? What's this? You know, just in English, forget just intuition. What's this term? Yeah? Claudio, right? That's right. It's the motion, the velocity of the center of mass. Sorry, not center of mass. We have no masses. Velocity of the center of the frisbee. Right? Good. Excellent. So we've taken care of this guy. What is this guy? What is this term?
Translation of the spider on the frisbee.
Yep, this is the translation of the spider on the frisbee. So now let's so we can write this as a velocity of the center, right? That's that term. Okay, we're going to recognize these terms more and more. You know, you could be completely brain dead about it and just kind of write it out, and you're perfectly right. It's completely okay, reasonable. You're done. Now I'm trying to tease out some intuition, and then when I do the next thing, this intuition becomes useful. Right? But so this is very fuzzy, hand wavy stuff I'm doing. So this is the velocity of the spider with respect to the frisbee. Is that correct? Now, do you notice a1 cosine theta plus a2 sine theta? a1 cosine theta plus a2 sine theta. Huh. Is that b1? Yeah? So this is L dot B1, right? Nice pattern to it, yeah? That makes sense because this is in fact the velocity of the spider with respect to frame B, right? And what is this term? Yeah, it's the rotational thingy, right? It's rotating and, you know, it's kind of doing this. So it's the lever arm L multiplied by theta dot, right? What's theta dot? It's the, yeah, it's angular velocity. But think about this. I never even used that word. I never even said angular velocity. Keep that in mind. So far, I have not said it. You said it first, right? Emilia said it first. I didn't say angular velocity. So you don't need angular velocity to do all this. It kind of comes out of the derivatives. It just so happens that theta dot shows up a lot in this math. So we call it angular velocity. We foist a kind of an official word on it. And then we use that to simplify the math. I'll do that today, right? But this is simply, actually, if you look at it, this is simply theta dot, which is the angular speed, L, Say it again? Who said that? Sorry? Oh, bless you. Sorry. So this is A1 minus A1 sine theta plus A2 cosine theta minus A1 sine theta plus, so it's B2. See that? Right? Which is kind of the, I won't write a word, I won't write it here, but it's kind of the angular velocity component, right, from the angular velocity. Got it? Right? If the angular velocity is 0, this term kind of goes away. So that was some of the intuition we got from this. Kind of makes sense. We did it purely with math. We didn't need any angular velocities, but we got the right answer, right? If I asked you to do this whole thing again using angular velocities, would you have gotten this answer? Yes. Nothing profound. The problem is when you get to the second derivatives, there are all these terms, Coriolis, centripetal, all this stuff, Euler, right? And you can miss it. But if you do it methodically as I did it, they'll all come out naturally, right? You know, there used to be an age when you had the Coriolis effect and you'd have to add it in. You had the centripetal effect and you'd have to add it in. The Euler effect, add it in. But we don't care for all that. We just do the math and it comes out. Done, right? But still, let's call out those terms. I won't call them all out because there's no room here. But this is actually A, acceleration point P, right? This term is actually B, acceleration of the spider. Okay? This guy, I won't write it, is the Coriolis term or Coriolis term. This is the Euler term. And this is the centripetal term. And that cosine theta, sine theta, they'll become just like B1 or B2 or something. And it'll all kind of fall into place. All right? So this was the intuition. So now that we have this there, I'm going to leave it, put it aside. We'll come back to it later. But now you have some intuition. And the two pieces of intuition are we never used an angular velocity. We never formally defined it. And yet we completed all this math. And we had a completely good answer. Right? What happened to the angular velocity? Why did we not need it? Anybody? How could we solve this problem without ever invoking an angular velocity? I'm sorry? Yeah. Yeah, that's part of the answer, yeah.
Because you're taking the velocity with respect to a different reference frame, so that changes the angle.
Yeah, look, here's what I did, folks. I just wrote the geometry out, and I took derivatives, and I get the answer. Right? Angular velocity is just a trick to simplify the math, but it's just the same thing. If I take derivatives, I'll get rate of change of the vector, and that's velocity, right? Do that again, I get acceleration. Angular velocity is just a trick to make the math simpler. Okay, done. Now, how about we solve another problem using this technique before we move on to angular velocities? Let me take a vote. Would you like to do that? Another problem? Gory detail, just nail it, you know? Yeah? You feel like, feel like that? Or is it too early in the morning? Okay, all right. Okay, you guys are going to help me solve this problem because I don't feel like yet. Because I've just had one coffee. Okay, so this problem that Ajay and I made this up. We were thinking about what other problem we could solve. So we made a problem up last night. Here's the problem. You have a pulley that is nailed into place on a wall. So it's not really a rotating pulley, okay? This is frozen. Now, from that, you have a rope hanging with a weight at the bottom. Okay? And you pull the weight up and you let go. What's the weight going to do? Well, first it's going to fall. Well, we pull it up tangentially like this, right? You kind of unwrap it and then you let go. So it looks like this. I pull it as far as I can because unwrapping, so it'll get longer, and then I let go. Right? So the pulley is going to fall. The weight's going to fall like this. It's not a perfect circle. It's kind of a spiral because it's winding up. Right? Comes here, and then it keeps going up. And then it'll go up, and eventually something's going to happen to it dynamically. Right? Now, we don't care about the dynamics. This is a kinematics problem. My question to you is, I would like to calculate the acceleration, the velocity and the acceleration of the pulley in terms of some parameters, geometric parameters. I want you to struggle with this a little bit and help me frame this problem. How would I go about it? What parameters capture the configuration of the system at any moment in time?
Say the radial distance from your block to the center of the pulley.
Just before you're given the radius of the pulley, all right? You're given that. and you're given the length of this cord at any given point in time, right? Or the initial length of the cord, and it'll wind up. So sorry, go ahead.
So the distance from the center of the pulley to the block changes?
Yeah. So that could be one thing you could use. You could take the distance from the center of the pulley to the block, and that could be one number, which if I give to you, you can completely describe to me the configuration of the system, right? Right? So when you parameterize a geometry, you're trying to find that one or two parameters with which you can completely describe the geometry. So that's a perfectly reasonable measure. But is there a more straightforward one? Yep, Claudio?
One line that goes from the center of the pulley to the tangential location of the string that's just going to rotate, and then just the distance, the length of y.
Okay, so you're saying this length. So I'm sorry, I didn't. What's your name? Amanda said this length, right? And Claudio's saying, why don't we just take this length? That's a little more intuitive, right? That's true. If I give you that length, which is the unwrapped length, the remaining length of the cord, then that's a way. If I give you that length, you know exactly where the pulley is, right? And you know where the entire system is. But is there an even simpler measure? Yep. Ted.
Use the angle.
Yeah. The even simpler measure. And by the way, all these are perfectly reasonable, and I could have solved the problem any of these ways. All right. So these are all completely correct answers. And now it's intuition. This is the only kind of place in dynamics where you need to exercise some intuition, where if you pick one parameter with respect to or another, the math just becomes easier, right? So it's Amanda was right, right? Claudia is right, and what Ted is suggesting is use the angle. So in fact, an even nicer or even more convenient measure is this angle. Get it? If I tell you what an angle is, I know where what the situation is for the system. I know where it is. Any questions about this? It's the angle between the last point of contact between the cord and this fixed pulley and the center of the pulley. If I tell you what that angle is, you know everything about the system, right? So let's say, so the way to think of kinematics is, as this thing does stuff, I take snapshots, right? And I need the number of parameters, I need enough parameters to pick which snapshot I'm in, right? If I tell you the angle, you nailed it, right? So the question now is, can you tell me in terms of theta what the position of that? So I'm going to redraw this, just kind of clean it up because there's a lot of scratching here. I'm going to redraw this. Let's use that angle as a metric because it makes the math simpler. It's nothing profound, but just makes the math simpler. Pretty good circle, huh? I have the circle thing going today. Good. I should do more circle problems. Okay. We're going to say this is just a point. We don't care about it, right? And this angle, we're going to call it theta. So if I capture this angle, then I know everything I need about this system. All right? Yes, no, get it? Okay. Any questions about this? Yeah.
How come we don't measure theta from the top of the pulley?
From the top of the pulley, I could.
Yeah.
There's no reason why I couldn't, right? I could certainly do it from the top of the pulley. I could measure theta from anywhere as long as it's a unique metric. As long as once I know the theta, there's only one solution to where which snapshot this thing is in. It's perfectly reasonable. I could do that. I didn't because, as you see, the math will be easier. That's all. It's just convenience, laziness. I just happen to know the back door, into this puzzle, right? But no reason why you couldn't do that. In general, I should tell you that framing problems as rotations makes the math easier. That's all. Okay? Any other questions? I want you to think about this a little bit. This is important. Now, if I tell you what the theta is, do you need to know what the exposed length is? Why not? Yeah. Yeah, if you know what the initial length is, which is a constant, if I tell you what the theta is, you know what the remaining length is, right? Right? So you don't need that. It's an additional thing. You don't need it. Right? In fact, that is, you'll see later, called a kinematic constraint. Okay? I could have treated this L and this theta as independent, but they're not. Right? So I could have had one, I could have just solved the problem as if L and theta were independent, and then later on stated the truth that, L is equal to some L naught minus R theta, right? Which is the wind up. Get it? But I don't have to do that. I can just do it explicitly. So in fact, if the length of the pulley, if the length of this cord, let's say that this is the initial condition. If this is L naught, then what is this length? Anybody? L is equal to L naught minus R theta. Okay? So with that one theta, I've captured everything about the geometry. I'm going slowly because you guys need to get this, and if you get kinematics, everything else follows. So nothing profound. I've just written it this way, and we're ready to go, right? Okay, now I ask you to tell me what the acceleration of this point P is. This is P. So what's the next thing we need to do? I want both the velocity and acceleration. What should you ask me? Yeah, with respect to what, right? Okay, I'm going to tell you. I want the acceleration with respect to the earth, to the ground to which this pulley is nailed. Okay, how would you do it? Say it again?
You want the acceleration of the mass, right?
Yeah, that point P, the kind of the center of the mass. Assume it's a point mass. Not that it's relevant, but just assume that. Okay? So, how do I start? What do I need to do? Say it again?
Find the position.
Yeah, find the position vector. Yeah, absolutely. Always. The first step, when you talk about a velocity or acceleration, it's simply the rate of change of a position vector, right? Whether it's getting longer or rotating or whatever, right? With respect to some frame. So let's write the position vector. Now, you can write the position vector directly, just using A1, A2, just use the math. Or, if you want to make your math a little simpler, you can introduce an intermediate frame. You don't have to. Just makes your math easier. That's all. Would you like to introduce an intermediate frame? Please say yes, because that's how I did the problem in my notes. So yes, please. Yes. Oh, yes. Thank you. That's a good idea. So, I knew you would agree. B1, B2. The intermediate frame here is simply aligned with the string. Okay? Yes? Makes sense, right? I just introduced an intermediate frame, and you'll see why. It just makes my math a little easier, right? Now, tell me what the position vector ROP is. Quick. Somebody. It's very easy. I know you know it, so just say it. Here, let me help you. Let me help you. Let me just say that let's call this point C. Okay? It's okay to be painstakingly simple with these things. In fact, the whole genius of dynamics is to be able to break down. When you see a problem, you will have a tendency to freeze. Right? What makes you, it's like a baseball player, a football player, whatever, right? What makes you a good engineer is your ability to fight that nausea, that panic. Okay? And then break the problem down into smaller steps, each of which is tractable. Yes?
Negative RB2, then L minus, or the L naught minus R sin theta is R. So R theta equals.
Perfect. Does everyone get this? It's very simple, right? Remember what I said, take a deep breath, break the problem down. ROP is actually this vector plus this vector, right? What is this vector? It is ROC, which is the radius, but in the negative B2 direction, right? That's this term. And then this vector is L in the B1 direction, which is, L naught minus R theta in the B1 direction. Done. Make sense? It's perfectly okay now to say, I don't get it, do it again. I'll do it again. Do you want to go sit next to Ajay there? It might be a little easier. There's a seat right there. Can you see? Okay. Yeah.
Does this count for changing data? Or does the frame in A, will that count for changing data?
So that's a very deep question Amanda asked. Does this count for changing theta? Is theta solid? Is it frozen? What's going on here, right? Where does the change come in? Yep.
So I think the B1 is the B frame is basically attached to the block, right? And then rotating with that.
That's right. So here's the deal, right? So this is the thing you need to understand. A is frozen. B is moving. Now, at an instant, B has an angle theta with A, right? But B is also moving. So the next instant, it's going to have a different angle. The next instant, it's going to have a different angle. So write it in that frozen state. Write the math out. And then when you take derivatives, don't assume theta dot is 0. Just give it some number, right? Call it theta dot. Get it? And that way you account for the fact that B is actually moving. Make sense, Amanda? Right? This is the sort of thing where you do more problems, it'll become, it gets into your gut. Right? So this is ROP. Believe it or not, this was the toughest part of the problem. And in fact, if you think about it, if you can do that kind of panic control thing, you can make this easy too. Once you have it here, you're done. So what is the acceleration of point P with respect to A? Can I write that? Can I write this? Yes, no, or maybe. Or only on Tuesdays? No, because B is a frame and it needs to be a point. The point P has a velocity. Yep, Andrew. Yeah.
What's the frame B attached to?
Aha, good. I said it fast, right? I said it correctly, I think, but it's easy to get confused. Here's what I attached B to. This is why there's an interesting problem. It's a transparency. Whenever you get confused about frames, think of transparencies. Rigidly attached to this block and always parallel to this remaining segment. Make sense? Right? Yep.
You can have A, B, B, like B, frame B moving with respect to frame A.
I can't do AVB. I got to do AVP.
Yeah, but
Yeah.
why can't you do AVB? Because wasn't in the last problem we have a moving frame B with respect to frame A?
It is a coincidence if all the points on a frame have the same velocity. If a frame has any rotation at all, then different points will have different velocities. So for me to say AVB is an incomplete statement. Get it? Of course, it is possible that my mistake, a coincidence makes my mistake not relevant. Okay? So if I'm a frame and I'm walking this way, you can certainly say AVB, right? Because my frame is moving, all the points are moving. But look, my arm isn't moving the same speed, right? Because I'm not a rigid body. But if I'm doing this, right, with respect to the earth, my head has a different velocity, my knee has a different velocity, right? So there's no AVB, it's AVP. The velocities are always of points. Very important. It'll all be intuitive, but once you do the homework, this will all be very intuitive. You've got to do it. Okay, so what do we do now? AVP, we're trying to find the velocity of point P. We're at the first step, already there. That was the hard part. What do we do now? Quick. Take the derivative, right? So the derivative is a d by dt of this guy. What's the problem? Yeah, right? Was that what you were going to say? Right? There's no problem per se. It's just that if I take the derivative of this basis vector with respect to frame A, it's not constant in it. It's kind of, you know, right? So I need to rewrite B and A, you know, in terms of A. And if I hadn't introduced an intermediary frame, right, I would have written everything in terms of A anyway, right? So you might say, Sanjay, why on earth did you introduce that intermediary frame if you're going to rewrite it? And that would be a fair question to ask. And the answer is, it just made it easier for me to write that vector. And later on, you'll see those intermediary frames help a heck of a lot. Right now, it's just a pain in the neck. Okay. So it is minus R. What is B2 in terms of A1 and A2? Anybody, please? Sorry, say it again. A1. Yeah. And then this becomes, I'm going to break the terms out, okay? What is B1? I can't see. Thank you. I need to take the derivative of all this with respect to time. But now all the A1s and A2s are constant in the A frame, right? So I'm good. And now it's just painful math. I'll do the velocity part, and I'll let you do the acceleration part. Okay, and just to warm you guys up, I'm actually going to have a snap quiz right now and have you do the accelerations. I'll do the velocities first to get you going. So, right, just painstaking math. Okay, I'm bored. So I just wrote that, and you guys can figure out what the acceleration is. Yes, the third term, I got them mixed up. The third term should be, this should be a sine, and that should be a cosine. Is that what you're saying, yeah. Levi? Yeah. If you if you know where to start, how many of you at least have gotten started and you know what to do? It's not such a big deal. Okay. Anyone who, if you want to talk to me later, if you want to ask me now, if you're not getting started, I can understand that. If you can't kind of get going because you don't know where to start, let me know. I'll come and tell you, or we can talk after class. It's not a big deal. This is new stuff, right? Ajay, are you done? You want to just put it on the board? Why don't you put it here? Because on it, huh? That's okay. If you're wrong, you're wrong. Ajay, do you mind putting it over there on the? Yeah, thanks. No, just put it here. Just put it in like all different terms. There's a lot of terms. I think you can break it up. Yeah. So Ajay is going to write the answer. All right, you can stop now. How many of you got going and was just working through the details? Okay. Anyone struggling with even getting started? It's reasonable and brave for you to say it, and we'll all be the better for it. Or if you can ask me later on, okay? So as Ajay writes this down, I just want to make a point. This is very unsubtle stuff. Do not look for a great amount of subtlety here. But it's perfectly correct. It's the long but totally robust way to do stuff. You will see in dynamics and in other fields, the long and the unsubtle way to do something is usually also in some ways the most mechanical way to do it. When you're, for example, analyzing the dynamics of a satellite with multiple moving parts, right? Equations will get long. It's only in exams that things cancel out, and that's because we arrange it to make your math easier. In real life, things might not cancel out. And then you have to get smart and make approximations and delete terms. Okay? When you analyze a really complicated satellite with multiple moving parts, this is how it looks. And there are computer programs known as symbolic computation engines, like Mathematica, Maple. Have you heard of these? Right? That do this for you. This first couple of weeks in class, you will have to go through it. You'll get it. And then we'll start pulling out the subtle insights. The problem with the insights is they're great, but you can also go completely wrong if you miscue. You understand? It's a shortcut. But you know how shortcuts are in Hansel and Gretel, right? You can get lost. So from here on, we're going to depart from this boring and mundane approach, which is actually beautiful in its own way, and start pulling out some insights and taking shortcuts. Okay? But when in doubt, you can fall back to this. This is fundamental. Is that good? Make sense? Okay? But the reason we want you to do this, so that you understand this works. It's painful, but it works. Thanks a lot, Ajay. Ajay just did it live in class because I made the problem up last night. Okay? And I solved it at 5 a.m. this morning. And I left my notes at home. So Ajay just did it live. There might be a typo here, but I doubt it because he's usually very good. And I can tell you that from the appearance, this is kind of what I got. And it's probably right. Okay? If you find an error, you can fix it. But this is the way to solve problems, in the most fundamental way to solve kinematics problems. Any questions? How many of you find this completely different from where you were heading with your answer? Anyone? Jarrell?
I mean, it's already like put together.
Yeah. Yeah, he digested it for you.
So I wouldn't even, like a lot of the beginning terms I can see are similar to some of the terms that I have.
Good. Yeah. If you finish it, they'll all come out. All right. Here's common pitfalls. When you take the derivative of a term like this, theta dot sine theta, right? It's going to break up into two terms, theta double dot sine theta plus theta dot squared cosine theta, right? So that's the kind of thing where you'll, if you're not careful, you fall off the bike. You got to kind of concentrate on the bike and stay balanced. Do the derivatives properly. Okay, does that answer your question, Gerald? Yep, Andrew?
Couldn't we have differentiated B1 and B2 and found out what the derivative of B1 and B2 were with respect to frame A? And then
Beautiful. I paid him to set me up because that's what we're going to do next. Okay, $5 later. Okay, all right. Okay. So I'm going to leave that up there. I'm going to delete this, erase this. And now we're going to start looking at a beautiful, beautiful thing along the lines of what Andrew was just saying for simplifying the math. We have 20 minutes, and I think we'll make a lot of progress. Okay. So I said to you earlier, I did all this without using the word angular velocity. Never used it. Right? Not once. The theta dot just fell out of my math, and you recognize that to be angular speed, but I never called it out. I never did omega r. Remember in physics you see omega r a lot? Right? And centripetal force is like omega squared. Centripetal acceleration is omega squared r. Remember that? I never called it out. It just fell out directly. Now let's call it out. So the first thing I'm going to do now is define the term angular velocity. So anyone take a stab at it? What's angular velocity? In the context of what we've said so far about frames. Anybody? What's your name? Katie. Sadie. Isn't there a singer by that name? Isn't there? Okay, sorry. Sade. Oh, sorry. Yeah. Perfect. That's exactly right. But there's a condition under which that might happen. For example, let's say I have one frame here, and I need something to toss. Right? I toss this in the air. Can you tell me what the angular velocity is at any point in time? Can you? Frame has to be what?
A polar frame of reference.
A polar frame of reference. Yeah, you're on the right track, actually. Right track. But I haven't used the word polar in the class. I don't want to use it. Anybody else? But Katie, you were right, actually. Sorry, Sadie. Sadie. Here's the answer. If, when you look at two frames, there is one line between those two frames that remains, I'm sorry, in both those frames, there are two lines that remain parallel, right? Then that means that one frame can be described as having an angular velocity with respect to the other and vice versa. Okay? So if this is a frame, and right now I'm rotating like this, then a vertical line through me and a vertical line through the frame remain parallel. That means I'm rotating. You understand? Now, if I take, there's a reason I brought my daughter's globe here, right? This thing's got 1 degree of freedom, right? It's got another degree of freedom, and I can rotate it this way. It's got 3 degrees of freedom. So if I do all simultaneously, right? You can say, well, Sanjay, there's no, what's the angular velocity, right? Now, there is some advanced geometry which I won't go into. You can actually find an angular velocity, but it turns out that in the worst case, I can say, hey, look, there's an angular velocity this way, and there's an intermediate frame, right? There's an angular velocity this way, and there's the two intermediate frames, and there's an angular velocity this way. So I can take any combination of motions and break it down into the composition of pairs of frames, each of which have an angular velocity with respect to each other. Get it? Now, you can ignore everything I just said, because in this class, we're going to remain in 2 dimensions. And in 2 dimensions, any 2 frames will always have the vertical axis parallel, right? Right? Yes? Right? If I take 2 transparencies, the vertical axis always remains parallel. So that means that there's always an angular velocity, which is the change in angle between the 2 frames, the rate of change of angle, right? And that's the angular velocity. So let me define angular velocity to you. the angular velocity we'll limit this definition to 2 dimensions. Very simple, right? Rate of change of angle between 2 frames. Okay? But that's just a scalar pointing in perpendicular direction. So Sadie is exactly right. So if you have one frame like this, A, another frame, kind of another transparency sliding in it, B, it could be moving, it could be rotating, it doesn't matter. At any instant in time, if you take the angle and see how much that's rotating, theta dot, and upmark it with the vertical axis, which could be B3 here, the same as A3 here, then angular velocity with respect to A of frame B is equal to theta dot A3 is equal to theta dot B3. Okay, that's a lot to say in one go, but I want you to stare at it for a second, and then we'll talk about it a little more. First of all, does that make sense? You know, I make mistakes on purpose sometimes. You need to stare at me and tell me if that makes sense or if it doesn't. Does it make sense? Yes or no? Yes? Anyone with a no? No is a reasonable answer. Could be. Small probability. Right. So that's what that is correct. It is essentially the rate of change of angle. Right? We saw theta dot show up many times. Remember, we saw theta dots here, right? So theta dot B3, which is the same as theta dot A3, because A3 and B3 are aligned when you look at 2-dimensional situations. That is the angular velocity. Now, in the past, we have shown we've used omega for angular velocity. We do the same here. Now let me ask you a question. How would you say this whole thing in English? Say it in English. Or French, for that matter. I like French. Yep.
Would it be like the angular velocity of A with respect to B would equal the rate of change of angle about A3?
You said it all right except one little thing. It's the angular velocity of B with respect to A, right? So here's how you say it. Remember the top left corner, this is always the frame with respect to which you're taking the angular velocity. Get it? So this is the angular velocity of frame B with respect to frame A. Okay? Get it? Now, yes, Ted.
Omega with B on the left and A on the right be the negative?
Ah, excellent. See, all these guys, I paid them off before class. So let's do a couple of kind of twists on this. Make sense? Look, with respect to the Earth, I'm rotating like this. If I freeze, the Earth seems to be rotating the other way to me, right? What is this? Ah, wow. No, what is it? Zero. Okay, so that's the angular velocity. Any questions? Now, we come back to Andrew's comment. He said, why don't we take, this derivative thing, we're doing this, right, painful way. Isn't there a way to take the derivative of B1, B2 once and for all, instead of converting everyone to A1 and A2 and just kind of making the math messy? So I'm going to tell you now, I'm going to answer that question. And this is very profound. And you might hear some music in your head when you hear this. Okay, be ready, because you'll be like, it's struck back by this vision that I'm going to paint in front of you. Okay, are you ready for a religious experience? Okay. I'm going to write a formula to give you an intuition, erase it and write the more general formula, because that's the one thing I want you to remember. So the intuitive stuff first. Promise me you won't write this down. It's correct, but I don't want your mind to enter this rut. I want you to think of it more generally. So put your pens away. You know why, where the shake hand comes from? Anybody?
It's to see if the other person has a weapon.
Yeah, right. So you'd put your weapons away. Do you know where cheers comes from? When you drink, you shouldn't drink, but if you did. You know where cheers comes from? Anybody? How do you know all this? Have you just been transported here from the medieval times? Oh, okay. Yes, so the idea was that if you're drinking with people used to poison each other a lot. The usual, right? So they would pour a little bit of drink into each other's glasses to make sure that you would both die, right? Assured mutual destruction. Okay. So this is the religious thing, right? You ready, right? Here's the deal. If you take a vector v that is fixed in frame B, it's fixed in frame B, the derivative with respect to frame A, remember this is fixed in B. Don't write this down. Is this. Ta-da. Okay. Just stare at it for a minute. I hope you're having this religious experience I promised, Gregorian chants, all that stuff, right? Okay. So a vector, if you take the cross product of a vector, if you take omega cross, A omega B cross of a vector, you're actually calculating the derivative of that vector with respect to this frame. It's beautiful. Okay, and here's why. Look at my arm, right? So it's going in a circle. So right here, if I move a little bit up, the difference is this little vector, right? So the derivative is kind of that vector. Isn't it at 90 degrees to this vector, right? But it's 90 along the plane. So if I take the cross product of that vector and this vector, won't I get this vector? Get it? It's very beautiful. Did everyone there get it? Let me do it again. So this is, my arm's going in a circle, right? So this is the plane. Okay, so my arm's going in a circle. So at this moment in time, snapshot, an instant later, snapshot, the motion of my arm was this, right? Think about it. First of all, that's perpendicular to this vector, and it's perpendicular to this vector, which is angular velocity. So if I take the cross product of this and this, I'm going to get 90 degrees, right? So in vector land, which is a space you're now inhabiting more and more comfortably, taking the derivative of a vector is kind of like taking the 90 degree to it. right? And the angular velocity, taking the cross product, which you've seen, is a way to just do that derivative. Now, you can pick up your pencils because I'll give you the even more profound version of this formula. And as a joke, this is not the official name for this, but in the notes as a joke. So please do not go to, Lockheed Martin or wherever you end up and use what I'm going to call it. We call it, in this class, and only for this class, the magic formula. Only because, to me, this is religion, okay? So the magic formula, which is kind of an extension of what I just wrote a minute ago, is A d by dt of a vector v is equal to b d by dt of that vector v plus a omega b cross that vector v. Okay, and the only difference from what I said earlier was I said imagine that vector was fixed in b, as in it didn't change in length or anything, right? So I'm generalizing it. So now imagine a vector that's actually changing in b, like becoming longer, like L in that example, right? It's getting longer. So it has a derivative in b as well. You can add it. Good? You understand? Now, why is this profound? Well, it's profound because I told you, but apart from that. Anybody? With you? That's right. That's right. Look, with this, if you need to calculate the derivative of something in frame A, but it's naturally expressed in frame B, no problem. Just add a correcting term and you're done. Got it? How much time do we have? We have about 5 minutes, 7 minutes. Do you think that's enough to solve that terrible Frisbee problem with this? Let's do it. Yep, Ted.
Right with respect to A? Or?
Say it again? That's not a velocity. That's a vector. Let's call it something else. That's just some vector. Just some random vector that's in B. Just some vector. It's not velocity. Please don't assume it's velocity. I run out of characters in the alphabet, right? And V's for vector and V's for velocity, so it could be confusing, but it's just a vector. I could use N, P, Q, whatever. It's not velocity. Okay, so let's look at this problem. Frisbee problem again. Okay, and the way I'm going to do it is I'm going to leave that live, erase this, and use that board, and that board. I want this so we can compare it, right? So that we end up with the same answer. So I'm going to erase all this. All this stuff is in the handout that is on the web that Ajay and I wrote up. So, what is the position vector of the spider? Quick. We have 5 minutes. Quick. Position vector of the spider with respect to from point A. Come on. Quick. U A1 plus V A2 plus L. Well, we can just write it in B. Just write it in B, okay? The intermediate frame. So it is L B1. This is the beast that we need to take the derivative of. The problem, the pesky term was this guy because we had to down convert it to A's, and that's what exploded on us, right? You don't have to do that anymore. So, what is A velocity of spider is equal to the derivative of this guy with respect to frame A, right? These two terms nothing special, right? Same as before. But it's this term where we end up with this kind of mismatch. right? And that's what exploded on us because of all the conversions. So what do we do now? Use the magic formula. And every time you use it, you'll hear this kind of music. It's cool. Okay, so they use the magic formula. So AVS tell me, what does it become? It's actually, oh, let's write it on full glory, right? It's equal to B d by dt LB1 plus A omega B cross LB1. Get it? That's usually the formula, the magic formula. Where instead of vector V, I have LB1, and I just, so essentially, I can, instead of taking this guy, I can take the derivative with respect to B and use this correction term. Get it? Yes? You've got to be really copacetic with this. Have you heard the word copacetic before? Yeah? Where did you hear it? Like, 7th grade? You know, I've been looking in the dictionary for years and I haven't found it. I learned it from a guy called Alex Slocum, who teaches W7. And he uses it all the time, and I just like it. Let's just define it, stipulate that it's a valid word. Okay, good. Okay, so you're copacetic with this? Good. Now, what is A omega B? Quick, in vector form, write it for me. In English, what is A omega B? It's what? Theta dot? Huh? Theta dot? A3 or B3. Remember, this guy is B1, so it's more convenient to write this as B3. Right? So this right? So AVS what is this? And what does this become? Was that a whole lot easier or what? Done. Is that the same answer as before? Yes? Isn't that beautiful? Now, how would you find A acceleration S? I have nearly done. 1 minute. Let's try and do it. I'll redo this in the next class, but I'm going to go really fast. And for those of you who are with me, something like this. Okay, we'll do this in the next class. I just wrote it really fast. Okay, we'll stop here. We'll pick it up in the next class. And if you don't understand that last bit, are you good with AVS? Everyone's good with it? I just did that again. All right, I just did it fast. We'll do it again in the next class. See you guys.